Welcome back, eNet 140 op-amp students. This is the third of three recorded lectures on Fiore's op-amps text chapter 3 on negative feedback. So when we left off, we had just derived an expression for the closed loop input impedance for an op-amp with a series parallel negative feedback network, and found, to our delight, that our input impedance rose proportional to the sacrifice factor or loop gain. So we can add an increase in input impedance for the series parallel configuration, in which we really want higher input impedance. Is one of those additional benefits to having negative feedback. So something else we're getting with our sacrifice of gain. So now we're going to look at the output end, and we're going to stay in our series parallel configuration of negative feedback. And for this, we are hoping that we're going to see a reduction in output impedance. That means that the signal will lose less as it leaves the op-amp, and that's what we want for this type of voltage amplification. So to do that, we're going to go back to a circuit model, kind of a similar one that we used before, to represent in a very, very simplified form, from an impedance standpoint, what's going on inside the innards of the op-amp, and then superimpose that on our feedback network. So like we did before, we're going to stand outside of the circuit here at this point, looking back into the circuit. And as you can see, we actually have a voltage source applied to the output, which might look a little strange. Like, don't we usually apply signals to the input? Well, yeah, if we're going to use the op-amp, we would. But we're representing a test signal with this. So we're going to put a little ping signal here at the output and just see what would happen to it if we shot it back into the op-amp looking for ground. So we're going to stand here at Zout SP, which is the output impedance, closed loop, series parallel, that we're going to derive, that expression. And we're going to look at what would happen to a little test signal, AC signal, as it moves from this point into the op-amp or around it. And that's the first thing we see, is that signal goes from our input point, it immediately hits our parallel bifurcation. Remember when we said that this is a series parallel? So here's the parallel part. So immediately we know we're going to have a little bit of a reduction in impedance because we have two paths to ground. So the signal can either enter the op-amp through the output end, flow through the output resistor, and down through our representational voltage source to an internal ground. And you've seen this is kind of you've seen this representation of the output portion of an op-amp before. This is kind of classic, where we have a little voltage source that is equal to the open loop gain times V feedback. And in this case, V feedback is V error, because we've grounded the non-inverting terminal. So if we look at this point over here, where we know that the voltage at this point relative to ground is V feedback, because we got a current flowing through the feedback resistor. So the voltage, the input voltage signal over our Z open loop resistor that we looked at in our last lecture really is, the drop over that is just V feedback, because we go to ground here. Again, this is not the way we'd configure the op-amp for use, but it's the way we're configuring it just for from the standpoint of looking at output impedance. So we're kind of looking from the output end back in. Okay, so there's the current path to ground through the op-amp. And by the way, there's a negative signal here, or a negative sign here, to denote the fact that the voltage signal is at the inverting terminal. So it's all taken up in that negative sign, all the inversion. Okay, going back to our fork in the road, the current that is coming from our test signal here could, in addition to entering the op-amp, it could go around it through the feedback network. So kind of through our little voltage divider, can flow through RF and RI straight to ground. So that's the easy path. So using Kirchhoff's current law, we can say that our I output, which is flowing from here, is the sum of the current that would enter the amplifier and go to ground that way, or plus the current that would go around the amplifier through the feedback network. So we can express the impedance or resistance at this point as the parallel combination of whatever the impedance is on this path, in parallel with whatever the impedance is on this path. Okay. The Z amplifier is going to take us a couple of steps to derive, but it's not really that hard because it's just a couple of things in series that we relate to other things we've already derived. ZF, which is our effective impedance of our two feedback resistors, that's really easy. They're just in series with each other. So we'll do a little bit of algebraic wrangling here, starting with our feedback network. So let's go ahead and derive an expression for ZF here in terms of things we know. This point here is at V output. That point is V feedback, which we've defined previously. So we can define IF in terms of V out minus V feedback divided by RF. And knowing that we really aren't going to get much current flowing through this, we can write another expression for IF. So we've got that over here. V out minus V feedback, voltage drop over the feedback resistor, is equal to the current flowing through the feedback resistor times its resistance. And then we can also express V out divided by that same current as equaling the series sum of the two. So that basically is, you can only say that if you don't have any current, any significant current going up through here. We've already said that in most cases Z in open loop is pretty big, so that's a fair assumption to make. So we can say that IF going through RF is the same as the current going through RI. So these two are in series with IF flowing through both. So that makes it pretty darn easy to get our ZF, our equivalent path to ground through the feedback network. So that's kind of trivial. So now we look at the impedance if we're going to take the path to ground through the amplifier coming in the output end. So we've repeated the innards circuitry from here. This is a little bit hard to write. We've kind of laid it all out. So this is our test signal, and over here this was our bifurcation point. So some of our output current went down through the feedback network, and so now we're just going to deal with a portion that went into the amplifier. So this is I amplifier. Well, as it goes in, it's going to flow through Z out open loop, our open loop output impedance, which is part of the op amp, and then down through this voltage source, which has a value of the open loop gain times V feedback, which is V error, given the configuration we had here that we just discussed. So we're just applying Ohm's law again. And just for simplicity, I've defined the voltage at this point as VB, and the voltage output is VA. So we can look at the voltage drop over the output resistor. We're going to apply Ohm's law again, is VA minus VB. And VB is negative open loop gain times V feedback, and VA is V out. So pretty easy. Well, the voltage drop over a resistor is also the current flowing through the resistor times its resistance. Hey, Ohm's law to the rescue again. So we're going to write all that out. So now we have an expression for the current flowing through the amplifier, or flowing in, the portion of the test signal current, times Z out open loop, which is intrinsic to the amplifier. This is something you can get off a spec sheet, equals the output voltage, which is our test signal voltage in this case, minus VB here, which is negative A open loop times V feedback. So we're just doing a lot of substituting in of quantities we've already derived and that we've denoted on our test circuit schematic. So we're relying really heavily on this this representational model of the op amp. And we had said that back in Chapter 1 that we would use a lot of very simple models of resistor networks and current and voltage sources to represent these very, very complicated circuits that are actually make up the insides of the op-amp. So that's what we're doing here. And please don't forget that these currents are test signal currents that we're sending in just for the purpose of defining our output impedance. We wouldn't use an op-amp this way. We kind of got it hooked up backwards. So just a little reminder there as we sling variables and algebra around here. So on that note, we're going to sling our V out open loop over to the other side of the equation and end up with an expression for that amplifier test current all by itself. Now we're going to do another substitution. We're going to remember that V feedback is also equal to V out times beta, beta being the relationship between these two resistors that we derived in the last lecture. So we're going to plop that in. Because remember, beta is nice because we define it in the circuit. Notice we're trying to write an expression for the output impedance in terms of things we can look up on a spreadsheet or we can define in the circuit ourselves. So things like the open loop gain here and the open loop output impedance, those are on spec sheets. We can look those up, and beta we can define depending on how we design the feedback circuit, in this case 2 resistors. So we're going in the direction of goodness here. So we drop in V out times beta for this V feedback, which we would otherwise have to test at a given test point. And so now we have the current, the test current going into the amplifier is the output voltage, or the test current output voltage, times, oh wow, there's our sacrifice factor again. 1 plus beta times open loop gain divided by the open loop output impedance. So we can again apply Ohm's law a little bit here by saying that, well, V out over Z out amplifier, we could define that as Z out, since we have the output and we have the input. We're going to apply Ohm's law again. So here's the output voltage, here's the current. We can define everything else here as being 1 over the effective impedance in that expression. So I'll go over that one more time because this is kind of a little Ohm's law application that makes our life really good. We've got voltage, current, and we know that V equals IR, and here's our I, here's our V. And so if we imagine everything else here being 1 over R, in this case it's 1 over Z output contribution from the amplifier in the closed loop configuration, but basically think of it as an R. You can write everything here as 1 over Z out amplifier. Okay, so we just applied Ohm's law again. So we can rearrange again and say, well, if that's the case, then, well, all of this stuff is 1 over Z out amplifier. So if I just flip this, invert it, take 1 over, I can say I have Z out amplifier, which is Z out open loop over that sacrifice factor. So in the closed loop condition with series parallel negative feedback, the contribution of the output impedance from the amplifier itself, not from the feedback network, just from the amplifier itself, that portion of the impedance is equal to whatever the open loop output impedance of that amplifier was, which we can look up on a spreadsheet, divided by the sacrifice factor, otherwise known as the loop gain. This is cool. And remember, this is in parallel with our feedback resistance, so the effective total output resistance is going to drop even more because we actually have those 2 paths to ground. So here we go, let's write it all together. So we can write a total expression for our output impedance closed loop in the series parallel configuration that we just defined is our impedance through the feedback network from the output point, all the way to ground through those resistors, in parallel with the impedance that we just defined to get to that internal ground point. So it's going to get even lower. So we've got that expression written here, Z feedback in parallel with Z amplifier. And so the Z feedback is just our RF plus RI, and then our Z amplifier is our open loop output impedance divided by our sacrifice factor. Okay, in practice, most people who design operational amplifiers design them to have a fairly low output impedance. That gives you better signal amplification, less distortion, less power usage, because you're outputting your amplified signal, so you don't want a big resistor there dropping it all out. We're going to take that small number and make it even smaller, because we're dividing by our sacrifice factor, which is always more than 1 and quite often considerably more than 1. So this path is very, very, very small compared to this path. So when we've got a parallel network and you've got one path that's the quickest path, easiest path to ground, most of the current tends to follow it. So we can make an approximation and say that the resistors in our feedback network, which remember those are selected in a range of like 10 to 100K, is going to be a lot more than this discounted, already low and discounted further output impedance through the op amp. So really we can approximate it as just this side. So our closed loop series parallel configuration, remember there's 3 other configurations of negative feedback closed loop, but this one's series parallel, we just derived, is going to be approximately equal to our open loop output impedance, findable on a spec sheet, divided by the sacrifice factor. Hey, that was what we wanted. Our input impedance we multiply by the sacrifice factor, and our output impedance we divide for the series parallel configuration negative feedback. This is another benefit to that gain that we sacrifice, because we always want this number to be low when we're trying to put an amplified signal out of it. So let's walk through an example, just throw some numbers on that. So somebody gives us an amplifier and says, well, we're gonna rig it up, and we know that our closed loop gain, if we put a series parallel negative feedback network on, needs to be 100, which is that's reasonably high for an SP negative feedback closed loop gain, but okay, that's what we want. And we're reading off the spec sheet. We have an open loop input impedance of 300,000 ohms, or 300 kilo ohms. We've got an output impedance of 100, so there's typical. Look, this is high and that's low. And we have an open loop gain of 50,000. So we've seen those kind of numbers before. So somebody wants to know what our input and output impedance are with the negative feedback, with our series parallel negative feedback, and only in the mid-band. We're not going to mess around with our performance out beyond the critical frequency, beyond our F2. So that should be pretty easy. So what do we need to know? Well, it would be nice to know the sacrifice factor, because if we knew that, all we have to do is multiply this number by the sacrifice factor and divide that number by the sacrifice factor. So how do we get the sacrifice factor from what we've been given? Well, luckily somebody went to a lot of trouble and quite likely experimentally measured this. This is closed loop gain for a particular feedback network. Who knows what they've got rigged up? But they've got a feedback network with a particular beta that they've constructed, and they've measured the gain and given it to us. Well, remember, one of the many definitions of sacrifice factor is open loop gain over closed loop gain. So all we have to do is take this number and divide it by that number, and we have our sacrifice factor, or loop gain, otherwise known as loop gain, capital S. So that's just what we do. So we take 50,000 divided by 100 is S, multiply it by the open loop input impedance, and we get the closed loop, and we get 150 mega ohms. This is great. This is now up in the level of what you would use for high fidelity instrumentation amplifiers. So we've taken a reasonably high performing voltage amplifier and turned it into something that's excellent. So we can look at thermocouple signals and things that are very, very small with that now. Likewise, we certainly don't want to lose any of that amplified signal on the output, and 100 ohms is a bit on the high side for an output impedance. We'd like to see that go down. So the nice thing is it will. It's going to go down by a couple orders of magnitude to 0.2 because we just threw in the sacrifice factor here as in the denominator. So easy peasy calculations. So you can see we went to some amount of trouble going through some KVLs and some real basic DC circuit models to derive the relationships between beta and our open loop op-amp properties and our closed loop properties. And having done that, again, caution, the series parallel negative feedback configuration, one of the four, but it's a popular one. It's the one you'll probably see the most. But nonetheless, as long as you're sure that you have that configuration, you can just use these formulas that you just derived within their limits. Just to walk through one of them, there is, even though you're going to extend, say, the midband frequency by using that negative feedback, eventually you're going to get to the point where that doesn't apply anymore. We start applying our sacrifice factor to a lower and lower open loop gain as we get further and further away from the midband, going to high frequencies, that relationship is no longer valid. So be cautious if you're operating like 5 decades beyond the midband. It's probably you're probably going to be limited by something else. But if you're in the midband or you're close to it, a decade or two on the high side, these equations should hold. And we'll say a few words about their limitations at the end. And then I believe Chapter 5 in Fiori, just glancing ahead, we'll go through more of the limitations on these assumptions. Okay, that aside, we got one more benefit to discuss. And I'll just zing right over here to our circuit model. So this little op-amp equivalent circuit only shows the output. It's very simplified. We're going to assume there's some kind of open loop resistive network here on the input, but we're not very concerned with it. We're just assuming we got some kind of input signal coming in. This one includes a second voltage source, V-distort, because a lot of real circuits have a significant source of voltage distortion on the output. And that's on the amplified signal. We really don't want that in our amplified signal. We want only the signal that we care about. So that distortion could maybe be an offset that would cause us to read a thermocouple voltage wrong and assume we have a higher or lower temperature, or read an incorrect amplitude on a sinusoidal signal, something like that, and get the wrong information. So these are bad. It would be really great if we could make these go down. Now, please do not confuse this distortion voltage source with common mode noise that's common to the inputs on our differential amplifier. This is a particular distortion voltage that's within the amplifier itself. It's not a common mode noise signal coming into the amplifier. It's being produced by the amplifier itself. So I don't have the details about what would produce it. That's beyond the scope of this course, but it's frequently there in bare naked amplifiers, in bare naked op amps without a feedback network. So they're pervasive enough that it made it into our textbook that we need to do what we can to reduce it. So we're just going to walk through the same kind of equations we did for closed loop gain, input and output impedance in the closed loop condition, and see what just simply having a negative feedback network in the series parallel configuration will do to that V distortion from the standpoint of what we're going to see at our output. And we'll cross our fingers and hope that that sacrifice factor maybe ends up dividing it and reducing it for us. Stay tuned, we'll see. Okay, so we will start again with our basic kind of KVLing our way from V out to the ground inside of our op amp. Those basic DC principles just keep coming. So we can say our V out is equal to, we're going to start with ground and move up. We have a voltage source that represents the open loop gain of the amplifier. Pretty basic. So open loop gain times our input signal. That's assuming one of those is probably our inverting terminal is at ground, and so we have signal coming in, so V difference is V in. Made it real simple. Then we have a bump up due to our distortion voltage source, the thing we don't want, and then we'll drop our voltage by whatever current is flowing through our V out open loop, and here we are at our output. We already talked about V out open loop. It may not be as small as it is when we add the feedback network, but it starts out pretty small. So we're going to assume that this I out times Z out open loop is small relative to these two voltage sources, because Z out open loop tends to be on the small side. So that's a fairly safe assumption. So we can say V out open loop, and this open loop, because there ain't no feedback network here, it's just the amplifier by itself, is equal to open loop gain times our input signal plus our distortion signal, which is coming from inside here. Okay, so we have an equation for that. Now let's add a feedback network and see what happens. We'll step through the same thing with a feedback network and KVL it. So we're going to start back here and KVL our way to ground. Well, this time we have two paths to ground. So we got that parallel network here. So we can stand here and say, well, V out is equal to A open loop times V error. Oh, it isn't just V in now. Ooh, there's one change. Without a feedback network, our differential signal applied to the amplifier was just V in. We assume we've grounded the inverting terminal. But now our inverting terminal is at V feedback, because we have a voltage source resulting from current flowing through our feedback resistor, which we've discussed before. So that changed in here. V error, it's V in minus V feedback. So that's a difference. This is the same, and we're again going to assume that this is small. So the current times this is also low. So we can write V out as open loop gain times V error plus the distortion voltage source. V error is defined as V in minus V feedback, and V feedback is very conveniently still V out times beta, all things we've already derived. So what we did was we KVL'd our way from ground, the internal ground in the amplifier, up here to V out. Same thing we just did, except we have V error instead of V in. So we'll take this with these substitutions and simplify a little bit and write it all together. So we can say that V out is open loop gain times V in minus V out times beta plus our distortion signal. It's coming from in here. Okay. We'll rearrange that a little bit more. Rearrange terms just a bit more. We're going to distribute the A open loop over this term and over that term. And then we're going to take V out times AOL, A open loop times beta. We're going to move it over the other side. Factor A out back out. And we'll be left with this term on this side, and then we just divide it back. And when we divide it back, we're dividing by everything on this side. So where I say rearrange, I'm talking you through the algebraic rearrangements that you use to get this. So when you divide this sacrifice factor back, having factored the V out and done all your algebraic rearrangements, you end up dividing this term as well, because you have to divide everything on both sides of the equation. So as we hoped, just by doing a KVL loop and some algebraic rearrangements, we find that V output with the feedback network gives us a reduction in the distortion voltage signal equal to 1 over the sacrifice factor. So we end up dividing by the sacrifice factor. We might also recognize that this whole concatenation of terms, our A open loop over 1 plus A open loop times beta, is our multiplier, our relationship between A closed loop gain and open loop gain. So we can say that this is equal to, V out is equal to ASP times V in plus V distortion over S. So we definitely got a reduction in our distortion signal. Now we can't directly equate V in and V out because we have the second term here, but we can show that we've reduced the distortion inherent in the output signal of the op amp by the sacrifice factor. So kind of to give a recap of the series parallel, when we bolt on a series parallel negative feedback network onto our bare naked op amp, and if that feedback network has a feedback fraction of beta, we can write an expression for loop gain or sacrifice factor in terms of open loop gain of the op amp and beta, which approximates to 1 over beta. We can take that sacrifice factor and relate our open loop properties to our closed loop properties with that series parallel combination. So open loop gain goes down to make closed loop gain. We divide by the sacrifice factor. Input impedance, we multiply by the sacrifice factor to get a higher input impedance. Output impedance, we divide by the sacrifice factor to get a lowered output impedance. And if we have any kind of distortion voltage sources in the output circuitry of the op amp, we will divide by the sacrifice factor to get their reduced contribution. So it's just a quick verbal summary of what the sacrifice factor that we just derived for a series parallel negative feedback network will do for all of our big performance parameters or characteristics of the op amp. Characteristics that lead to performance parameters. Okay, 2 more pages, 3 more pages, almost there. We're going to do a real quick touch on the second most popular negative feedback configuration. Remember, there's 4. We hit 1, the series parallel, most commonly used for voltage amplification. It's flip. The parallel series is, not surprisingly, the most popular one used for current amplification. So kind of like the current amplification you get in a BJT. So now we're going to take a look at that, and here's our quick schematic. So what is parallel series? Well, if we're looking at a current signal coming in, so we have an I in instead of a V in, you can see that the current is going to branch. The signal that's coming in is going to branch to something going into the amplifier and then something going around it. Now that was true for the output in our series parallel, but now we see we've got this parallel branch on the input, hence parallel. But on the output, current's only got one place to go. Your voltage output signal is only defined in terms of the voltage drop over this load. You don't have an output voltage that can go out to a circuit and then portion of it is fed back. The whole thing is fed back. And if you want an output voltage signal, you better just measure the voltage drop over that load resistor. So you have a series configuration through the feedback network on the output. So parallel on the in, series on the out, hence parallel series or PS. So we're going to have a PS subscript instead of the SP to denote all of our closed loop properties. So doing that, we're going to define our current ratio, closed loop gain, as I out divided by I in. And these arrow directions are somewhat arbitrary, but they'll get important later on when we start defining things based on which terminal inverting or non-inverting we're going in and out of. We have the same relationships we did with voltage, so we can define a feedback current in terms of our feedback fraction times the total output current. So rather than harvesting a portion of the output voltage with a voltage divider, we're going to harvest a portion of that output current with a current divider. So some of that output current is going to flow through the load resistor, and we can take off a voltage signal. It's going to come into our feedback network, and we're going to send some of it to ground. We're going to send some of it back into the inverting terminal, and so there's your negative feedback mechanism. We're going to take a portion of the output, what we didn't send to ground, jam it into the inverting terminal, which is what we need for negative feedback. Kirchhoff's current law still works, so the total current going in is going to equal the current going into the amplifier, into the inverting terminal here, plus the current that's going down into the feedback network. And we can say that our I out, using our typical gain relationships, is now going to equal that current flowing into the amplifier that would come back out at ground times our open loop gain. So this is very analogous to our V out equaling our V difference, or our V error in the case of a network with the SP configuration times the open loop gain in the amplifier. So basically it's flip side, except everything's really written in terms of current. Okay, since the non-inverting terminal is grounded, I amplifier is the differential input. So again, this is at ground, so whatever flows in here ends up having to go to ground right there. So it's really simple. So now we're just going to do some plug and chug and define I in. We're going to plug expressions back into our Kirchhoff's current law expression. So I in is going to equal I out over a open loop. Instead of I amp, we're going to use this equation, plop it in there, and then instead of saying I feedback, we're going to use this relationship and say beta times I out. So you have I in plus a couple expressions, each of which include an I out. We'll factor that I out, pun intended, and end up with an I out over I in expression that we can relate to our closed loop gain and everything that was left over here. So we do some more algebraic rearrangement, and we can say that APS, closed loop gain in the parallel series negative feedback configuration, equals doggone it, isn't that familiar? The same thing it equaled with series parallel. Open loop gain over 1 plus open loop gain times beta, and this bottom factor being our familiar beloved sacrifice factor, approximatable to 1 over beta. So when written in terms of current, our parallel series closed loop gain is the same as the series parallel. And I will leave it to you to walk through an example where somebody uses an input current source and sends it into a parallel series negative feedback network, and figure out or verify that the gain is indeed greater than or equal to 10, which they needed for whatever they were doing with their load. I think they were going to put a digital multimeter, and didn't have a high enough signal, so they're going to amplify it, and you need to verify that it meets the requirements to be read by the digital multimeter. You can step through that. This is Fiori chapter 3, example 4, example 3.4. You can step through that. So we'll touch on just really quick, we'll walk through the math that enables us to get the input and output impedances for the parallel series negative feedback configuration. So this is the analog to what we did with series parallel, and it's kind of important we take a quick look at this because it's inverted. So if we look at, again, one of these circuit models representing a simple op amp, the input impedance of it anyway, we're not even looking at the circuitry for the output. So we're just going to say what happens to our effective or closed loop input impedance when we put this parallel series network on. So not surprising, we're going to define some terms and do some KVLs. So we have our input current signal coming into this point. It's going to split because we got a parallel input. Some's going to go down through the feedback network to ground, and the rest is going to flow into the amplifier, I amp, into the amplifier, and it's going to flow through our open loop input impedance, whatever that may be, but we can look it up on the spec sheet, to ground. So we've got it coming in on the inverting and coming out of the non-inverting to ground. So this is our circuit model of what we think the open loop input impedance is, and then our feedback network. So we'll define Zin parallel series, otherwise known as Zn closed loop, with the parallel series negative feedback network. We're going to apply Ohm's law. We're going to say, well, that is V at the input terminal right here coming out of our current source, whatever that voltage is, divided by the total current we're putting in. So R equals V over I. But we can define Vn in terms of this input resistor. So we can say, well, if I look at the top of this, there's no other resistances, no other opportunities for voltage drop. So I can define V at the same place I have my input current coming out as the voltage drop over the open loop input impedance here. So, oh, well, the current flowing through this is I amp, so the voltage drop over this resistor is just Zn open loop times the current flowing through it, which is I amp, which is Vn. So we have that here. So Zn closed loop is current flowing into the amplifier times the open loop input impedance, spec sheet readable, divided by the total current that we're sending in. So we can rearrange that a little bit again, and remember that, not rearrange, apologies, we can invoke a second equation, our Kirchhoff's current law expression at this point. And then we can insert another expression for I feedback that we already defined, which is beta times I amp times AOL. And these are previously defined, so I'm not going to go back and explain them this time, but you can look back and prove to yourself that these are true, probably in the previous expression for closed loop gain derivation for parallel series, and we end up with total input current is the current flowing through the amplifier times sacrifice factor again. But we have this relationship that relates open loop input impedance to total current and current going into the amplifier, that ratio. So we can rearrange this, grab that, use the sacrifice factor, and come up with a total expression for our parallel series input impedance in terms of the spec sheet readable input impedance divided by the sacrifice factor. So not surprisingly, when we put a negative feedback network on an op amp and we arrange it in parallel series, we reduce the input we reduce the input impedance by the sacrifice factor rather than increasing it. We can use a similar current sourced model, and this is analogous to the series voltage source that we used when we derived the output impedance for the series parallel closed loop configuration. So this is basically the same kind of circuit model, except we use a current source and a parallel output resistor. This is totally equivalent, and so we use this to define an output current. And so I will leave it to you all to step through the same kind of algebra that we did up here and verify the relationship between our open loop output impedance and our closed loop with parallel series and the sacrifice factor. And it's important to note that, again, you multiply. So this is the opposite relationship that we saw with series parallel. So the effect of our negative feedback network on our closed loop impedances depends on the configuration of the network. We can raise or lower the input or output impedances by our sacrifice factor depending on how we've hooked up the feedback network. So if we hook it up as parallel series, we're going to reduce the input impedance, raise the output impedance. If we hook our negative feedback network up series parallel, we're going to raise the input impedance and lower the output impedance. And again, this is good in both ways, because if we're using a parallel series feedback network, it's because we're going for current gain, and we will get a better signal if we reduce that input impedance and raise the output. So if you go back to your, I think some of this was early chapter 2 and chapter 1, the objectives of amplification, we want to preserve our signal, minimize our losses. So if we're looking at a voltage gain, we want high input impedance, low output impedance. Current gain, it's the inverse. And so negative feedback effectively gives us what we want, regardless of what kind of amplification we're going for. But we do have to bear in mind what type we want when we're designing the network. So do not use a parallel series feedback network if you're going for voltage gain. You'll be doing yourself a big disservice. So we're not going to go into the other two, the series, and parallel feedback networks. They're out there. We will pick them up in chapter 4 in very simplified form, where we basically leverage all of the characteristics of feedback to produce an idealized op-amp performance that will look a little bit strange, but will be essential to us to simplify our circuit analysis and allow us to do a lot of wild things with op-amps and make very simple calculations. So stay tuned for those second 2 of the 4 negative feedback configurations. But so far we've covered the 2 most frequently used: series parallel for voltage gain and parallel series for current gain. Okay, last slide and we're almost done. Limits of negative feedback. Fiore talks about how at this point you'll believe negative feedback can do everything, including slice bread and tie your shoes. Unfortunately, no, it can't. It does have its limitations, and I've highlighted here the 2 biggest ones to remember. If we're talking about increasing bandwidth, remember it was so nice. We would, when we went up a decade in frequency beyond the mid-band range, we had that example where we showed that we only had a 1% loss in closed loop gain, but we had an order of magnitude loss in open loop gain. And we're thinking, oh great, we can extend the mid-band ad to infinity. No, we can't. As you continue to go further and further beyond the mid-band, your S factor that you're multiplying by, it itself starts to get smaller. Because remember, S, at least in that series parallel configuration, includes 1 plus A open loop times beta. As your A open loop gets small, you can't assume that it's not going to change. So your S will start to drop, and so that salubrious effect of the S multiplier will be lost, and so your closed loop gain will start to drop as well. And at that point you're probably also going to get other effects from principles of physics that we haven't even included here. So just be aware that that's gonna be a factor. You could probably do a back of the envelope calculation and say, well, if my open loop gain is decreased by maybe 4 orders of magnitude, what's my S? Maybe there's other things that would limit my amplifier use past then. Of course, 4 decades of frequency increase is probably plenty to be extending. The other thing to remember is fundamental amplifier characteristics aren't affected. So if you're clipping, because for whatever reason you're asking the amplifier to output a voltage versus ground that's more than the supply, it's going to give you the supply minus a bit. It's not going to change the capacitances due to the junctions in the semiconducting devices intrinsic to the amplifier. So things like how fast it can change direction, slew rate, is not going to change. We can't compensate for that with negative feedback. And the one that I don't have listed here, remember, when you reduce distortion, the derivation we went through, remember that is only applicable to distortion signals that are inherent to the external circuit of the op amp. If you have noise coming in on the input, you will be relying on your differential amplifier portion of your op amp, which is an open loop characteristic, to remove that. So don't rely on feedback for that. Okay, this is the end of chapter 3, and for those of you who are taking this course in winter 2020, you will probably have an exam coming up that covers chapters 2 and 3. So please use this as a study guide, and please step through these derivations. If you're weak on the algebra, do it yourself so you see it and you know it. Do not use those equations blindly. It's as you can see, there's a lot of places where S is multiplied or divided, and it's real easy if you're taking an exam or you're doing calcs out in the field in your first job to forget where it is. If you derive things yourself, starting with circuit models, it's hard to go wrong. KVL and Kirchhoff's current law will not fail you here. So go ahead and use those, and please work through some of the problems. Fiore's got some great examples and some great problem sets at the end. Very applied, very simple. We'll really lock these concepts in. So we'll see you hopefully in a few days with postings for lectures for chapter 4, where we will roll all of this complicated derivations of negative feedback into some idealized behavioral assumptions for op amps and then use them in some cool circuits. See you then.